Heave-ho, and listen to my tale of a plank of wood and a
I'm gonna make this unlucky scallywag walk the plank. He better hope I did my calculations correctly, or this whole board is gonna rotate and he's gonna fall to the ground. Now this plank here hangs over the edge of the table by about 1 meter, as you can see here. In fact, it's exactly 1 meter. All right, now get up there, you scallywag. Come on, get. Okay, now I gotta be careful here, because for this trick to work, I do have to be holding firmly down on this end so that this board does not rotate. So I'm applying a downward force to counteract the rotation caused by this scallywag. But if I were to let go, that would be utterly disastrous, because then there would be no force to... Uh-oh. So why didn't my victim fall down when I let go of this side of the plank? It comes down to torque, also known as rotational force. It turns out that this board's weight all by itself is enough to completely resist the rotation caused by his force or his weight at the edge of the board. Now let's dive into the details so we can understand how I could do this experiment and know with 100% confidence that my volunteer would never fall down and get injured, unless of course they lost their balance. So this is a diagram of the setup, and it turns out that this board that I had is a 4x12, which means it's 4 inches in one dimension and 12 inches in the other dimension. So it's a pretty thick plank. And that 4x12 board was 15 feet long. And that length is really what matters here. So we have a 15-foot long board, and it's balanced like so. This little image here, this represents the fulcrum, which is actually the edge of the table. So this is where the edge of the table was. Anything past that was sticking off the table. And if you recall, that distance was 1 meter exactly, which is approximately 3.42 feet. So I'm gonna label that as 3.42 feet. And if this is a 15-foot board, that means the other distance, so from where the table started to the other end of that board, that must have been 11.58 feet. So now we have our two distances from either side of the fulcrum. And remember, the fulcrum is just the point of rotation. So at the end of the day, we absolutely do not want this board to rotate around the edge of the table, because that is what would cause the volunteer to fall down to the ground and get injured. Now, some other information aside from the length of the board, we know, or I know through my research, that it has a unit weight of 10.42 pounds per foot. That means each foot of length of this board weighs 10.42 pounds. The next thing to observe is that there are exactly 3 forces acting on this board, or at least we could model that as 3 forces. The first force is due to the weight of my volunteer, and that person had a weight of approximately 160 pounds. So I put their weight here as 160 pounds, and it's acting as a point force right at the edge of the board. Now, technically, you could argue that his feet were shifted a little bit from the edge, and so really that force would have been a little bit closer. But to model it at the edge of the board, we're being extra conservative because we're accounting for the maximum amount of rotation from that force. And that force is acting a distance of 1 meter away from the fulcrum, or you could just say 3.42 feet, because I'm going to use English imperial units for this problem. And the second force is the weight of this board that's hanging over the edge. And that force I'm going to call F1 in my diagram. Now, technically, that is a continuous force, because remember that each foot of this board has a weight to it, but you could take that continuous force and model it as a point force that's exactly halfway to the edge of the board. So in other words, we're going to say all of that weight is concentrated right in the middle, and that's what we're calling F1. Now, the last force in our diagram is all of the weight on this side of the fulcrum, so the board that's on the table and sticking out the other side. You could calculate all of that weight and model that as a single force right in the center of that part of the board. And we're going to call that F2. So that's the force of the weight of this board holding it down on the other side. And essentially what we want is the rotation caused by my volunteer's weight and by the weight of this part of the board. Those two rotations need to be less than the rotation caused by the weight of the board on this side. So what is F1? Well, this force, the weight of this section of the board, is equal to the unit weight of that board itself. In other words, 10.42 pounds per foot of board multiplied by the length of that part of the board. So it's 10.42 times 3.42 feet. And if you do that calculation, you get F1, which is 35.64 pounds. That means this part of the board is producing a downward force that's equal to about 35 pounds. Now, what is F2? It's the same process, so it's the unit weight of the board, so 10.42 pounds per foot of board times 11.58 feet of board on that side of the table, and that gives you a F2 value equal to 120.66 pounds. So that part of the board weighs substantially more, and that's good because we want more rotation on that side to save the life of our volunteer. And now we're ready to calculate the solution. So ultimately what we want is the torque on the left side of the board, the torque over here, to be, I shouldn't say equal, it needs to be less than or equal to the torque on the right side of the board. Remember, torque is rotational force. So we want the overall torque that's causing rotation on this side of the board to be less than or equal to the overall rotational force on that side of the board. So what do we have here? Well, torque is force times distance. So the first force is this weight of the volunteer, that's 160 pounds. So I'm gonna write 160 pounds. And the distance from that force to the fulcrum is 3.42 feet. So I'll say times 3.42 feet. And so this force times this distance creates the first torque around this fulcrum. Plus, there's one more torque caused by F1, so that's 35.64 pounds. So plus 35.64 pounds times its distance away from the fulcrum. And remember, we're modeling that force halfway from the edge. So that means it would be half of 3.42, which is 1.71 feet. So times 1.71 feet. And that has to be less than or equal to the torque on that side of the board, which is this force, F2, 120.66 pounds, multiplied by the distance to that force, which again is half the distance to the edge of the board. So that's gonna be, 5.79 feet? 5.79 feet. And so now we can solve this and just prove that the overall torque on the left side is less than the overall torque on the right side, and that would show why in our demonstration the board did not tip over. Now, if I use my calculator to punch in all these numbers on the left side of the expression, I'm gonna get 160 pounds times 3.42 feet plus 35.64 pounds times 1.71 feet. And so the overall torque on the left side of this board, due to the volunteer's weight and the weight of the board itself, gives me 608.14. So this is 608.14 feet pounds. Feet pounds are the unit of rotational force, or the unit of torque. So we have 608.14 feet pounds of torque on the left side, and on the right side, I can punch it in the calculator again. So 120.66 pounds multiplied by 5.79 feet. And I have an overall torque of 698.62. 698.62 feet pounds. And so notice that the overall torque on the other side of the fulcrum is much higher than the torque caused by my volunteer and the weight of the board on this side, which is good because that means the board is not going to tip. You probably noticed that there was about 90 feet-pounds of torque more on this side compared to this side, which means we had a little bit of wiggle room. I could have technically pulled this board out a little bit further to make it more dramatic, but I'm, an engineer and a physicist at heart, so I always like to be a little bit conservative just in case. Remember, safety first. There's actually an equation that I was able to derive, and if I use this equation, I can figure out exactly how much board I need to make sure this thing doesn't tip. And so the equation looks like this. It says X equals L over 2 times W over lambda L plus 1. And so I need to explain what these variables mean for you to understand how to use the equation. X represents the distance from the fulcrum to the edge. So X is how much board can you hang over the table. So if you were trying this at home, which you shouldn't, you could actually calculate that with this equation. And so L is the length of the board. It is the total length of the board from end to end. In my case, it was 15 feet, but you could use any length of board, and that's the beauty of this equation. 2 is just the number 2. W is the weight of the person. So again, the beauty of this formula is you can use it for any person you want. So in my case, W was 160 pounds, but you could have a different person and a different weight in your formula. Lambda, this symbol here, remember that is the unit weight of the board. So I had a board that was 4 by 12, but you could have a 2 by 12, a 2 by 8, a 2 by 10. And so those different board thicknesses are going to have different unit weights. So you could really use any board you want, but of course you want Lambda to be as big as possible, so it's always better to use a thicker, more heavy board, and that will give you a bigger value here. L again is the length of the board, so I would put a 15 here, 15 feet, and then +1. So basically for any type of board of any length, of any weight, and any person as a volunteer, you can actually calculate the maximum amount of length that you can hang your board over the table to ensure that this thing does not rotate.
Heave-ho, and listen to my tale of a plank of wood and a hardy